Welcome and thank you for joining us for this afternoon's live panel discussion, which forms part of the Data Centers Ireland Virtual Festival. My name is Hugh Robinson and I'm the Exhibition Director for Data Centers Ireland, which, due to the pandemic, cannot be physically held this year. The Data Centers Ireland Virtual Festival consists of 10 live panel discussions, 2 per day over the course of this week, featuring industry leaders and experts discussing key areas affecting data centers, both in Ireland and internationally. As well as the live panel discussions, the festival also has a range of on-demand content which can be accessed through the Data Centers Ireland website. This afternoon's webinar is entitled Liquid versus Air Cooling, Pros and Cons, Where and When, and features an exceptional panel of experts. If you would like to ask questions through the presentation, please put these in the chat box and they shall be addressed at the end of the discussion. This webinar will be recorded and uploaded onto the Data Centers Ireland website as additional on-demand content. The moderator for this afternoon's panel discussion is Dr. John Summers. John is a scientific leader in data centers at the Research Institutes of Sweden and adjunct professor at Luleå University of Technology, Sweden, as well as a senior lecturer in thermofluids at the University of Leeds. So without further ado, I shall hand you over to John. John.
Thanks very much, Hugh. Thanks for that introduction. Hopefully you can all hear okay. Yes, so a provocative title besets us, and we've got a stellar lineup here of panelists who are going to talk probably in some kind of uniform manner. I bet that we're going to come to some agreement towards the end of this, because we're all engineers at the end of the day and we're solving problems. So if I could have the slide that introduces the 4 panelists, please. Should come up any moment now, so that you have, there we go. So, so we have Daniel Pope, who's the co-founder and CEO of Submarine Motion Cooling. Matt Evans from Airedale, who Airedale is a company that does everything in the thermal arena. Dr. Tony Robinson, who's a co-founder and CSO at Nexalus, and Alan Beresford, founder and owner of EcoCooling, and the master of fresh air, I must say. So let's get this show on the road. But first of all, before we do get the panelists to introduce themselves, their company and their particular role in the form of air or liquid cooling, I wanted to just briefly go through what we mean by liquid cooling, because sometimes that gets a little bit confusing. So this is a schematic of the different cooling methods that are used in data centers today. It's a high-level schematic. It doesn't talk about anything in detail in terms of how we remove the heat from the more detailed aspects of it. But to the far top left there, we've got full air cooling. Sometimes that uses an economizer, which is using water. So in a sense, some people could argue it's a form of liquid cooling because we use water to deal with challenging conditions outside. But this is the whole concept of this is to bring fresh air into the data center or indirectly exchange air with the outside air through a heat exchanger. In the middle of the top line there, we've got what we call peripheral liquid cooling. So this is liquid at the edge of the data center. So this is your traditional computer room air handling units, computer room air conditioning units. So the liquids can be a refrigerant or chilled water. Now we get into what some people would call liquid cooling, because we're bringing the liquids closer to the IT. So if I fail to say that, the actual rack of 4 pink boxes represents the IT. So what we're doing here on the top right is bringing the liquid closer to the IT, and you can see there's a little blue and red arrow there, which indicates that there's exchange air cooling, but we're actually got proximity, liquids close to the IT. So this will be in-row cooling, rear door heat exchangers, or on top of the rack or below the rack, where you used air as the principal heat transfer medium. This is kind of what some people refer to as the indirect liquid cooling. Then the bottom left, we have direct liquid cooling. And this is where now you see the liquid loop has invaded the IT space. And that's a challenge sometimes for data centers when we start to invade the IT space. So direct liquid cooling in this case is where you have still a little bit of air to deal with. So you might use a rear door heat exchanger as well with this so that you can get all your heat into liquid. But this is a combination of direct to chip or variants of that and air cooling. And the final bottom right is total liquid cooling. This is where we harvest all of the heat from the IT and all of the peripheral devices through liquid. And this can be immersion or some other form of total liquid cooling. So if you picture this for the moment, I wanted to go through and introduce the panel. Maybe we leave this slide up so that they can refer to it when they talk about their technology. So if I could go to first in my list on the video, there is Dr. Tony Robinson from Nexalus. So Tony, over to you. Please introduce yourself.
Hi, I'm unmuted, I think, yeah?
Yes, you are.
Okay, super. So hi, everyone. My name is Tony Robinson, and I'm an associate professor in the Department of Mechanical and Manufacturing Engineering at Trinity College Dublin. And just for a bit of sort of context where this comes from, it goes back to my graduate research back in Canada. 25 years or so, I've been specializing my research in experimental and computational thermofluid science. So I study heat transfer, fluid mechanics, thermodynamics, and fundamental and applied physics, or energy physics and technology. So basically, I dedicate most of my adult work life to understanding sort of basic nature of heat and fluid flow, so that we can basically develop better technologies. And over that time, I've done a lot, everything from evaporation physics and microgravity for the European Space Agency, deep space voyage tech, to generating electricity from biomass cook stoves in sub-Saharan Africa with Irish Aid. And but what's consistent across all of these is that it's solving important problems by leveraging sort of scientific knowledge and practice into engineering and new technology development. And that's kind of where Nexalus came from. And that's why I'm here talking to you virtually today as the co-founder and chief scientific officer of Nexalus. So the big question, what is it that Nexalus does? So our mission is to provide high-tech, sustainable electronics thermal management solutions. And in doing that, we prioritize performance and profit, but always the planet as well. So we see data centers as not just a challenging electronics cooling problem, which it is. We also see data centers as a challenging energy problem, which they are. And so our tech, which you can see, check out at nexalus.com, it all underpins super high performance liquid cooling, direct liquid cooling, but with this necessary twist of full heat recovery. And this is what creates this clean energy revenue stream out of the heat currently being wasted. So we're all about engineering for the circular economy and doing this in a way that doesn't compromise performance and utility. And I'll say, when people see our solution, and many people have from all different sectors, it's really, when they see this surgical cooling with capturing of heat right at the server level, they always say, surely this has been done before. And my kind of answer to that is, hey, we put people on the moon before we put wheels on suitcases, right? So, and I don't mean that to be sarcastic or, funny, but it is a little funny. But it just really highlights that if you don't let yourself kind of be inhibited by any blinders that come along with the way it's been done before, then you have this unique opportunity to do it the right way for the first time, and that's what we're trying to do.
Okay, thanks, Tony. Yeah, there's a few things you brought up there that will come up in the discussion later, so food for thought for people. So if I may move on to Alan Beresford. Alan, please, would you introduce yourself and the company and and a little bit about the cooling methods that we're going to be talking about later. And you're on mute at the moment. Yeah. Or are you? No? Okay.
Yeah.
Oh, you're
Hi,
fine. You're fine.
Yeah. Hi, I'm Alan Mason, MD and owner of EcoCooling. I've spent now nearly 10 years using direct fresh air cooling of data centers, both using adiabatic evaporative cooling and just pure ventilation. One of the real reasons I'm here today is to share this experience of doing 350 data centers, 3,000 telco installations, 150 megawatts of high performance computing, GPUs and ASICs, as well as working very closely with John on the Bowden type data center, which was for the last 3 years, we have used direct fresh air in a Horizon 2020, a European funded scheme, which helped us build a 500 kilowatt technical toy to play with. So John and I, for the last 3 years, have had a serious piece of lab scale equipment to experiment with and challenge some of our thinking, and we've learned quite a lot from it. So hopefully I'll be able to share some of that with you today. Okay.
Great, thanks, Alan. I don't know whether there's something you can do with your microphone or change the microphone, but you are a little bit broken up. I don't know whether anybody else has the same problem. But check that in a minute, Alan. Yeah, but thanks for the introduction. So if I move on to Matt Evans at Airedale, please could you introduce yourself? I know Airedale probably operates in all of these corners on this map.
Yeah, I guess so. Thanks, John. So yeah, Matt Evans. I'm currently the technical account manager for Airedale, as you say. I think traditionally we've been an air cooling company. Very much focused on all sorts of air cooling, be it in rack, on rack, perimeter, crack units, fan walls, all that sort of stuff. I say traditionally because we are genuinely continually innovating in the space, and we're trying to improve not just what we already offer, trying to make that better, but also expand our horizons, and as you say, try and go into maybe all of those boxes on that sheet. We've got a big plan as a business, as part of our parent company, Modine. We're aiming to become more and more relied upon, not just throughout the UK, but we're expanding quite rapidly into Europe and also America. That's a new venture for us as a business. So yeah, our current focus, we are aligned with what we feel are the market forces, which are, I believe, air is the future, purely just from what is going on. But with all this said, I'm very excited and interested in the more exotic and interesting solutions out there. Being an engineer, it's a lot of fun, to be honest, to keep up to date with the market and the technology. And kind of similar to what Tony was saying, for me, it's all about looking to push the envelope a little bit more. We're kind of not in the same realm that Tony is in terms of doing it right first time. We're doing sort of iterative improvements in a lot of our products and solutions. But I think it's important for myself and for the business that we always try and better what's been done before. We want to play, personally and as a business again, play some part in driving the industry to becoming, more of a contributor to carbon reduction as a whole.
Great, thanks, Matt. Yeah, some inspiring words there for future engineers, maybe. Yeah, so it is fun. Yeah, let's try and get more of these youngsters to join the team. Yeah. So last but not least, Daniel Pope from Submer, please do introduce yourself. I know you're 1 hour ahead of everybody else here, aren't you?
Yes,
So,
I'm lucky enough to be based in, not today, very sunny Barcelona, but yeah. So Daniel Pope, I'm the CEO and co-founder of Submer, a company that we set up to tackle, I guess, total liquid cooling. So the bottom right square in this slide. The company was founded in 2015, but prior to that, my background is in data center design and operation. I've run a couple of data center businesses in the past, where I've had to go through the pain of scaling the business and building multiple facilities that were trying to improve the previous one, I guess, trying to make things easier. One of the biggest pains always being cooling, I guess. Our vision is changing the medium that surrounds the IT equipment. And we compare that to, I guess, what we consider one of the most perfect machines on Earth, which is the human brain and the cerebral fluid that cools that brain. So we're applying, I guess, a similar principle to cooling IT equipment by using immersion cooling. The vision of the company is probably slightly broader than just cooling. We're looking at enabling next generation cooling, not just for data, but also for energy intense environments. And we might talk a little bit about that down the road. And also we've gone down the path of automation in the data center space. So really looking at robotics, with the goal, I guess, of delivering technology that enables a new generation of ultra dense, ultra efficient, but also autonomous infrastructure. So that's me.
Okay, thanks very much, Daniel. Yeah, so we're going to consider quite a few topics, and I think, well, just to give you a heads up of what kind of topics we're going to be looking at. I mean, the efficiency question is always going to come up, so we're going to discuss that at some point, and what solutions will be driven, should be driven by IT, or how we drive solutions from the IT. Then there's always the issue of cost around this, which we'll cover. And then the issue, well, it's the word cooling is very empty, and for, you know, we should be talking about heat transfer so that we end up using the heat. So we're going to touch upon heat reuse within this as well, and the variations between what you can do with air and liquid. And then there are some environmental considerations, and I think we also have to have our eye on the future all the time. So we will cover these points. So my first question really is about efficiency. Now, let me start this by saying one of the problems we have with computing is, and trying to say relate it to the efficiency of, say, a motor vehicle, is that when you go from A to B with a car, it depends how quickly you want to get there. Now, you could talk about the amount of joules of energy you consume to get from A to B. If you do it really fast, then you're going to use more energy. If you do it slower, or you do it at the optimal speed, then you're going to get there with less energy. So with that in mind, you know, when we're looking at energy efficiency, but from the perspective of removing the heat from this annoying heat generating components within the data center, could you explain a little bit about efficiency from your perspective? So I'm not going to go back in the same order again. So I'm going to go straight to you, Matt, on this one first. So if you'd like to give us some views on this, yeah.
Yeah, it's a good point, John. You know, the old efficiency thing, I was thinking the same thing. You know, what do you classify as efficiency? Is it purely a metric in terms of how much energy you're using directly? You know, on that note, I guess the full topic of this, you know, liquid versus air. Air cooling, you know, I'll put it out there just to please Daniel, if not a lot of other people. You know, direct liquid cooling, immersion cooling, direct to chip, that sort of stuff, very close coupled, rear doors, that sort of stuff. You know, it is more efficient than what people are considering to be typical air cooling. You know, large cracks, moving lots of air and the like. That said, though, it's really not that far off immersion these days. You know, even with mechanical systems, so those with, you know, refrigeration, chillers, you know, things like that. You know, peak power does not equal the true real world efficiency. So it's very easy to sort of say, oh, well, you know, you're running chillers, so, you know, you're going to blow loads of power. Most of the year with free cooling chillers, you know, we're easily getting down to, you know, PUEs. And I know that PUE isn't the greatest, but for a comparison metric, yeah, we're getting down to like sort of 1.1. Now look at where we've been in the past with that. We've been over 3, you know, with DX systems, cracks, all that sort of stuff. You know, the efficiency for me is, you know, people are confident in what air systems can do. They garner decades of experience to provide the solutions that we have today. You know, they're efficient in terms of pounds per kilowatt, and I can't stress that enough. You know, they are a very, very cost-effective solution to, I would say, 99.9% of data centers issues today. I bet you there is less than, 1/10 of 1% that actually require anything more than 10 to 15 kilowatts a rack. And we can still do more than that with air, but just as an example, So I think the air cooling, it's efficient from a lot of points.
Okay, Matt. Yeah, I mean, now I'm debating whether I should bring Alan in to support you on that, or whether I should let maybe Daniel or Tony countenance that. So maybe Daniel, yes.
Yeah, absolutely.
Give us your view on what's just been said. Yeah.
Yeah, I mean the 10 to 15 kilowatts per rack is the challenge that we have of having designed everything around air and working with those densities where air makes sense and everyone feels comfortable with it. Designing environments for humans to walk around and also feel comfortable in them, right? So the whole server package or the IT package has been designed for that. And that's something that can be easily challenged if you change the medium. Like in one of those racks, why not deploy 250 kilowatts if you can? I guess it's just the path that we haven't taken. What I would say is, from an efficiency perspective, what immersion brings to the table, apart from the PUE, where there's lots of studies already that it's extremely low, like in the range of 1.03, 1.04, I think more beneficial to that, and something that is directly connected to PUE, where you'll just see server vendors throw more power into the fans of the systems to, let's say, have that hidden cooling cost, which is considered IT. That in itself represents 10 to 25% of power consumption for a data center, the fans that are in the systems. So something that I guess immersion cooling can completely get rid of. There's other things like the zero water consumption that can be leveraged by closed water loops, which is another humongous benefit that immersion can bring to the table, I guess. Maybe some people are not so challenged in wetter and colder regions, but there's a lot of data centers being built in very warm climates right now. And well, we'll see if fresh air cooling works so well in those environments. And then I guess delivering this efficiency and benefits anywhere on the globe is another key factor that immersion can bring. It's very hard to design, I guess, a unique system, primary and secondary cooling that you can deploy, be it in Ireland or be it in Dubai with the same architecture. That's something that immersion does allow you to do, and it allows you to achieve the exact same PUE and efficiency in those two environments, for example. So flexibility, I guess. That would be my take.
Okay, Daniel, you've raised a couple of interesting points there that I think really Alan should come in on, and that is PUEs as low as 1.04. I mean, Alan loves the PUE. I think but also you mentioned the fact that maybe the air cooling guys are cheating because they're increasing the energy consumption by the fans in the servers, which means the PUE is improving. And also the challenges of deploying data centers in hotter regions using direct fresh air. Alan, what do you think?
Well, if you look at efficiency, what we've done at Bowden Type Data Center, we've done two things. First, as part of the brief from the EU, we had to measure PUE, because that's what people understand. What we did there was try and get the world to think in a joined up manner. So we concentrated on chip temperatures. And in the open compute pod, which John looked after, his guys rewrote the internal firmware to control the fan speeds on the servers to react to the incoming air temperature to maintain a constant chip temperature. Now that does two things. One, it makes the chip temperature nice and constant and consistent, but also it slows the server fans down. Now you mentioned, a significant part of these parasitic loads are the server fans. If you start slowing things down, the energy of these fans follow a cube rule: half the speed, 12.5% of the energy. This makes dramatic differences. So stage one, get the chip temperature right and get the fans on the servers to manage that. And then secondly, what we call holistic control, get all our fans in our refrigeration or air cooling system to follow that. Now, when you do that on conventional equipment, it has actually proved to be quite straightforward to get an air cooling partial PUE of 1.01. Okay.
In the polar circle, though, I guess, no?
Yeah, so lots of things came out of this, right? Okay, so a guy called James Hamilton of Amazon many years ago gave a Google presentation on their energy forum, and he said any component within a modern server can actually survive in the hottest place on earth, Death Valley. So he said it's only a mechanical engineering exercise to get enough heat transfer out of that component using the air. So what we did at the Bowden Type Data Center, we've got a range of equipment, some open compute, conventional CPU. We've got 150 kilowatts of GPU rigs and 180 kilowatts of ASICs. Without changing any of the heat transfer equipment within it, what we're able to do is, by making sure we've got the control of the chip temperature right and reacting correctly and enough airflow, we actually are able to lift the supply temperatures as high as 40 degrees centigrade, still maintaining chip temperatures in this range 70 to 75. Okay, which surprised us, which suggested other systems, be it fresh air, direct or indirect, maybe weren't providing this equipment with the right amount of airflow, including the internal server fan control algorithms. Also within that, we did actually also push to extremes. So whilst the open compute was conventional density, we have achieved the equivalent of about 40 kilowatts a rack on GPUs and 75 kilowatts a rack on ASICs using just fresh air. Okay, up to those crazy levels of air on temperature as well. So what we've done there is, by exploiting some simple principles of physics, particularly this cube rule, is that I accept what you're saying in Arctic, the air is going to be easy, but we don't actually do that. We never run conventional IT below 15 degrees centigrade and the ASICs at 10. So run as cold as you can for as long as you can to increase the actual equipment reliability, and then react on the warm days or the hot days with the appropriate airflow controls to maintain chip temperatures. So getting this formula for, as you said, Daniel, about getting things to work all over the world, Dubai or Luleå, right? Then it's about understanding that heat transfer, and maybe just as you guys in the liquid cooling, the air cooling guys, we're now saying we now maybe want to start reconfiguring servers to match what we're doing. Okay, let's get the appropriate heat sinks, fans, etc. algorithms in place for that. So the Bowden Type Data Center did demonstrate that efficiency PUE can be achieved at reliability, but also, just to throw one last thing into the mix, what we've also done is start to measure efficiency in energy consumed by useful work. How many teraflops per joule can you actually really do? Because that ultimately is the real measure of efficiency. Useful work done, how much energy is consumed. And that is where the big pot of gold really is. That's enough for me for the time being, John. Is that okay?
Thanks, Alan. Yes, I mean, to add to that, Alan, the thing that we did discover is that as you go for a target chip temperature, and so we slowed down the fans, we traded the fan energy for increased energy consumption by the IT due to current leakage, because as you increase the temperature, then you see something else happening in the IT system. So it does raise the question, run hot. ASHRAE says run hotter. We're saying in the W classification, run as hot as you can, because you can reuse your heat, which is something we're going to talk about later. What is the good temperature to run at? I mean, our view, Alan, I think what we came up with is that a good way to operate IT is to keep it at a single fixed temperature, irrespective of the workload, because you get less thermal shocking of the electronics. But of course, you have very little thermal inertia with air. It's terrible with the thermal inertia. Anyway, Tony, you haven't had your 5 minutes of fame yet on this subject.
Yeah, so I'm a heat transfer guy, right? that's where I started, and I guess I have to say that it seems like with air, it's like the 100-mile Olympic race. It's like you're beating it by tenths of a second. I know that we can get it down, and Google's average is 1.15, and maybe it can be 10, but it can be knocked over the head with liquid. I mean, when we're talking about the scale of the data centers and the energy consumption that they have, I mean, that 5%, 6%, 7% is still a lot of energy. I mean, the quantity of energy, and I suppose our take from the liquid point of view, it's the way we kind of run our research, is that we look at the heat transfer at the chip, right? Because if we can develop a technology at the chip level cooling, which is, however you want to say it, an extraordinarily low thermal impedance, then you don't need as much liquid to cool it, right? And that's the whole thing. And I know you said about the hydraulic, it's the hydraulic power, right? Our pressure drop goes as the square of your flow rate, and energy is cubed. You want to be down at this bottom part of the curve. Like, you can't be operating up over here. So we have to engineer a solution that's really high performance, so we can operate down in the bottom part of this curve. And that's how you engineer to this unity, PUE or efficiency. It's all about getting to unity, and you have to decrease that hydraulic cost. Or, I mean, for liquids or for water, it's a hydraulic cost. Your pumping power needs to be down. So what we did is we focused on the heat transfer and developing, this microjet cooling technology for the chips that is so highly effective that we need a trickle of liquid to do it, which means our pressure drop or our hydraulic pumping power, if whoever is close to being negligible. And that's how we can get the PUEs down, with the submersed cooling people, down in the 1.0 and change, right? And I guess the other thing and you'll hear this from me a lot, whether today or later, is that and I know this is a topic, and I hate to get into it right now, but that's only one efficiency, right? I mean, if we look at data centers from a thermodynamic efficiency, it's zero, right? Because we're wasting everything as heat. And can we afford to do that right now when there's 200 terawatt hours plus, being dissipated as heat? The financial efficiency in the context of heat, wasting heat is literally wasting money. Heat is a commodity. Space, space and real estate, for, let's say, 10 kilowatts per rack, which is quite honestly pretty low compared to what you can do with easily with liquid, and like the submersion, we're not limited to cold climate geographical locations. So I guess in this whole context of efficiency is, should we be sticking our finger on one efficiency? If we're looking at things like performance, profit, planet, are there not efficiencies that kind of line up under each one of those P's? performance, profit, and planet. And anyway, so it's my opinion, I guess, is that the efficiency, when we think about efficiency, we should be drawing our circle out a little bit wider than just necessarily the energy efficiency, but certainly it's the first point of call.
Okay, yeah, very good point, Tony. I mean, this is probably an apt point to bring up, because I think as engineers, and I guess we probably all sit in the thermal engineering sector because we're dealing with heat transfer with microelectronics. We're starting to talk about the formula racing car type approach, trying to get 10 seconds off the lap time. But really the real problem with efficiency is the fact that it's the one of the PUE, it's how big is the one or how small is the one, so it's, when you talk about efficiency, isn't it terrible that these systems have to produce so much heat when it's not actually what they're designed to do? They're supposed to produce digital services. And it brings up something that came up in LinkedIn, and I got involved with it, as I usually do. Somebody, I can say who it is. I'm sure if Emma's on the line, Emma Fryer, she will laugh at this. But I mean, basically, she said, look at the IT industry. We've had 7 orders of magnitude in efficiency in the IT space over 30 years. If the same was true of the aviation industry, we would be flying from New York to London on a teaspoon of Calpol. Now, I responded to that and I said, well, look, the thing is it's about efficiency headroom. Aero engines are 80% efficient on the basis that the calorific value of the fuel, 80% of it is converted into kinetic energy, which is motion, which is what you want. You want to get from A to B. Whereas if you look at data centers, you pump all this electricity into them, and the percentage of that is converted into digital information, which you can measure using Shannon's principle, how much energy is in that stream of information, it's 0.03% efficient. So look at the headroom we have in the IT space. But of course, that's not our domain. We have to deal with what we're given, in terms of the IT space. So obviously, IT is changing, and we're reaching a crossroads in terms of IT. We're not sure where this is going to go over the next 10 years because Moore's law is challenged. Shrinking it further we're reaching the physical limits. And for those that are interested, you should look up Rock's law as well as Moore's law. Rock's law says we're going to run out of money before we run out of physics because it's getting more expensive. How much should we consider the IT that's going into the data center as part of the cooling solution? So I think this is quite an important thing. So maybe I'm going to end up going back the same order, but I think it's probably important that we hear from Daniel at this point, if I may. Over to you, Daniel.
Yeah, I mean, obviously immersion has a lot of benefits if we can influence the IT manufacturers, given that any equipment designed for air environment is extremely low density compared to what you can run in a immersion environment. And the benefits of actually being able to push that bar are substantial, meaning we could easily generate water which is directly usable in a district heating environment, for example, just with the exercise of designing equipment that is capable of withstanding those temperatures, because you can cool them. And because the CPUs already operate at 100 degrees centigrade. So I guess just by optimizing some components on the IT design and capturing that heat, there's substantial benefits there. With immersion systems today, I mean, it's really easy to dissipate 3 kilowatts per server U. We're working already in the range of 6 and 8 kilowatts per server U. The only space where we see that capability is, again, in the Formula One of computing, so supercomputing environments, where it is quite typical to see an 80 kilowatt rack. So it is possible. by optimizing the IT equipment. I guess the key resides in putting together the right hardware setup that allows you to monetize the savings on the facility side, meaning if you are collecting all that heat, and in the case of immersion, up to 99% of the heat generated by the IT, the savings are not in the efficiency. They're on, and we're going to get to that, I guess, but they're on repurposing that heat, reusing it for something valuable instead of just putting it out there again without monetizing it. And when the industry realizes that today there's already utility companies that are building massive district heating infrastructure, and that they're already purchasing that heat at between 30 to 50% the cost at which they sold it, it makes no sense to talk about PUE and all other stuff, because the TCO is just completely different.
Okay, yes, you're touching upon a topic that we're going to come up against later with reusing the heat. But I mean, I guess that for some people on the line now will probably be thinking, well, that means that data centers have got to start dealing with refrigerants and compressors again. Matt, the compressor in the data center, what do you, I mean, from the point of view, I guess this is veering off the IT question, but as you're coming more from the I guess from the envelope around the IT space, what do you see in terms of cooling technologies for that are driven by IT?
Well, it's interesting because, you know, I've said it before, and I guess I'm going to end up saying it again, so I'll get it in quick. I do think that the immersion, not so much the direct-to-chip, but the immersion aspect or technology is kind of, it's kind of like trying to browbeat a solution where there isn't really a problem. You know, in common data center servers, there isn't a continuous increase in density. There isn't a problem with, you know, cooling. I think there's a good reason why people aren't putting, you know, 3 kilowatts on a single U, because it's just not feasible to do so from a packaging perspective, and also it's just not required. You know, you look at the immersion stuff, with the exception of isotope, which is kind of in a vertical arrangement, you're actually using more floor space up. You know, if you're doing an equivalent, let's say you're doing 100 kilowatts a rack, like Alan was saying, you put that in a horizontal bath. Apologies if bath isn't the right term, but you know, you put that in a horizontal space, then it's taking up more floor space. Now, part of the interesting part actually of what you were saying, John, is I'm working on a project at the minute, which is 30 megawatts worth of racks at 295 kilowatts a rack. You know, that's pretty sizable stuff. That's supercomputing stuff, and that can't be done without the use of chillers, because the density is so high that the direct-to-chip system needs water around 24 to 25 degrees. You know, so that kind of blows that out of, you know, into, you know, you have air here, and then you've got absolute extreme here, and immersion sits in this kind of, to me at least, this middle part that doesn't really exist at all. It's kind of like a black hole of nothingness. I really can't see it taking off purely on people trying to sell it as a solution to density. I think Daniel's points about it being an easy driver for heat reuse, I know we're going to get onto that. I think that's very valid, and it is the most obvious choice from a sort of synced up perspective. You know, I think it's the easiest way to recapture heat, and because of that, it's got a long future. But at the minute, trying to shoehorn it in on the basis that IT equipment requires it, I just don't buy it.
One thing that I'd like to talk about, there's, you know, in terms of efficiency, there's efficiency of, well, John hates this grubby commercial money side of things, right? Okay, so one KPI which is obviously important, which a lot of the guys talk about, is how many dollars per megawatt. Now, if you've got your conventional data center costing $5 million a megawatt to construct, I mean, literally as we're speaking, I just sent an email for a 15 megawatt unit, which will cost, that's GPUs, which fully built will cost under $300,000 a megawatt to build, and have a PUE of 1.02, 1.01 something. that CapEx, OpEx thing is actually very relevant to a lot of these guys who are deploying the next challenges to the hyperscale.
Okay, Alan, yeah. Tony, you wanted to say something. You put your hand up.
Yeah. Sorry. Unmuting there. Yeah.
Yeah, you're unmuted, yeah.
Yeah, so I think it's a bit, we're sort of crossing a lot of, and I'm probably to blame for it, for crossing into the energy and the performance kind of side. But I suppose from an Exelis point of view, we first of all, we solve the toughest computer cooling problems that exist. And that's from high-end gaming, overclocking, and HPC, right? So that's where we start our tech development. We throw everything in our scientific and engineering toolbox at the problem. We're literally going right down to the cores on the processors. That's the level of interrogation that we have to go down to develop the tech. So like this is our Formula One. It's a Mars rover, so to speak, where we kind of get, pushed to limits that make you interrogate every nook and cranny. You have to understand the physics. And then that's where the solution that didn't exist comes from, right? And this kind of goes back to the right solution for the first time. And so this is where our water cooling tech comes from, but also other things, like new thermal interface material, which we haven't talked about, which is part of the cooling problem. About new precision mounting and assembly technology that we've developed because we've been really focusing on how CPUs are cooled and the best way to get heat out of them. And this is, so like sort of Formula One is to consumer automobiles, like that's where ABS brakes came from, as an example. All of this trickles down into our data center tech, right? And the whole thing about solving problems which are harder than the problem you're faced with is you get this headroom to do other things, right? So by solving these crazy, highly overclocked, gaming computer, overclocking computer problems, when we turn it down into the data center space where the heat fluxes aren't nearly as high, we have this overhead for things like turning down the flow rate for this is where our heat recovery comes from. You know what I mean? It's because we've developed this overhead. But at the same time, like we were talking about with the HPCs and these heat flux going high, like you're saying, Matt, it really, if the liquid cooling solution is tapped out and you need to chill it, the first point of call, from my opinion, would be to look at the liquid cooling. How can that be more, is the liquid cooling that's in that system effective enough? Because if the thermal impedance of the system at the chip is low enough, then you can use the water that's hotter. Do you know what I mean? So of course, anything can be cooled by turning down the temperature of your coolant. But that doesn't mean there's not engineering that can be done at the place where the cooling is actually required, like on the chip. And that's one of the reasons why what we do is, in terms of this IT-driven solutions, is we go, okay, what's the hardest problem to solve? And we get our ideas from there, and then we like I said, we map that down and trickle that down into the data center space.
But the problem is what temperature should we be operating these microprocessors at? Because if it is, again, if it is about turning down the temperature because we don't want to waste so much energy in actually digital processing, then surely that is something that we should head for. But at the same time, we've got
you can get both on that one, right? Because you can, there's two ways. If you have a heat exchanger on a chip, there's two ways to improve the heat transfer. You can reduce the temperature of your coolant,
yep,
or you can reduce your thermal resistance or your thermal impedance of your heat exchanger. Those are the two ones that you have to play.
Mm-hmm.
And so what I'm saying is that, as from a heat transfer designer point of view, and I've done telecoms, domestic comfort heating, automotive heat exchanger design that use air, right? And of course they use air because air was the right coolant for those problems. But in the data center space, where you're looking at these heat fluxes that are driving up and such, and you need this overhead to do other things like heat recovery, then it's liquid, and you have to solve the hard problems. And the hard problems, our Formula One is overclocking high-speed computing and gaming. And that's where in terms of IT-driven solutions, those are going to trickle down into PCs, and it's going to trickle down into data center tech.
Yeah, I mean, this argument has been going on for a long time. It's the liquid cooling is a specialized. They're saying it's a specialized approach to dealing with high performance computing or overclocked CPUs because you're generating tremendous amounts of heat flux. Now let's look at this in a different way. We talked about earlier on about the fact that Moore's law is challenged now. So where do we go with this technology? We've got so much inertia with the digital revolution. Are we going to be putting in, Matt, you mentioned three kilowatts per 1U as maybe a target. Maybe this will come about one day if we start increasing the amount of the heat fluxes in these devices. So surely it's about reusing the energy, and that's where I wanted to go next because we've covered this a number of times. So Alan, what can we do with air and the reuse of the thermal energy? Is it possible to do anything? Yeah.
There are three answers to that, and two of them rhyme with no. Okay. Unfortunately, most of the deployment isn't close enough to normal residential properties to use these things, use waste heat for district heating schemes and things like that. Okay, and particularly the giant installations. Maybe at a small scale, maybe at an edge level, it could be happen. But in terms of major installation, there's no connectivity. The other thing about direct air is that we make the most heat when we don't want it. We have the most heat rejection during the summer when we don't want it. We have the most rejection during the middle of the day when we least need it for a domestic scheme. So when we need the most heating during the middle of the night in winter, we're recycling 85–90% of our energy, so it doesn't work. However, what we have done at Bowden Type Data Center, we did a trial where we used the waste heat to dry biomass. Now, it is crazy that we actually use gas-fired systems to dry biomass. That's standard, to get it down to a moisture level that's required for domestic biomass boilers. Now, if we use that waste heat whenever it is made available and effectively buffer it in the dry biomass, that then converts that heat into useful work. Okay. One that we obviously did learn from the Bowden Type Data Center was because we were able to elevate the exhaust temperatures, having air at 40 or 50 degrees centigrade exhaust is obviously a lot better at drying. As Tony will know, the psychrometric curve also does that, and every degree centigrade you add on to that exhaust temperature, the amount of evaporation it can create, it goes up stratospherically, logarithmically, exponentially, whatever. Right. So there are uses for waste heat, and it was a successful trial. But I personally think the biggest opportunities in some of these drying operations for practical commercial operations that stand alone without any external funding or grant or subsidies. That's my opinion, and I've looked at lots of things trying to do, because it's obviously a big thing for us all.
Okay, Alan, well said. I guess that's an interesting point. Daniel, I mean, so we're seeing these heat fluxes go up. So I think liquid cooling is coming of age, isn't it? I think we all agree that sometimes that we have to use liquid cooling in some solutions, and I guess you have come across a lot of different takes on this. But what about the heat reuse? Are you finding that your solutions are being more used? Your solution is being more used in the heat reuse scenario, or is it just because I think, and to deal with one of the questions in the chat, is it actually ending up in parts of the world where it is actually more challenging to get rid of the heat?
So I'd say we're seeing both things, because we're seeing the benefits of heat reuse in the colder regions, while as we're seeing the benefits of closed loop zero water consumption in the hotter regions with immersion cooling. I mean, what I would say is that the ASHRAE Technical Committee 9.9, it's really allowed us to easily achieve 60-degree water from immersion systems today with the hardware that's available today. And again, with the densities that hardware allows for, which, coming back to the density topic of the rack versus the tanks, I can rebate that one pretty quickly, but I don't want to go back to it. I mean, our expectation is that as end customers, DC operators, server manufacturers see the benefits of heat reuse, that the IT will be designed to leverage heat reuse, and that will just help raise the return water that we're capable of achieving, getting it closer to what's directly usable by district heating systems. But because of the intrinsic design of immersion cooling, you can capture 99% of the heat in water compared to air-based systems. And that obviously, I guess, is one of the biggest benefits of the technology. We've already seen real examples of utility companies repurchasing energy, as I mentioned, for 30–50% of the actual cost for which they sold it a few seconds before to the data center. If you combine those two benefits, you could be slashing your electricity bill in half again, when you're already running the facility at a PUE of 1.03. We're convinced that this is the holy grail and that only immersion cooling can bring this. And we're not just talking sustainability here. We're talking massive TCO savings. So it's not the hype and the something that looks fancy or something that has no use case for it. It's going to be it's the next step in TCO benefit compared to I guess moving from the 3.0 PUE to where we are today. This is the next level. This is from where we're moving today, the 1.1 in Boden, to a climate positive data center.
1.01.
1.01, yeah, with the penguins dancing around there.
Yes, Alan. There's some advantages of a cold climate there. Yeah.
No, we do achieve that in lots of other places as well now. Now, the other thing that I would like to mention about this total cost ownership, things like that, is that in the olden days when I was a lad, we used to design data centers with like a 15 or 20-year life for them. Okay. I'm not sure that's the case nowadays. I don't really know how long these facilities are going to be functioning for. And when you take a total view on the investment, is particularly the IT equipment could change so much over the next 3 or 4 years. What do we do to accommodate anything that these guys might throw at us? If you go to Derek Webster's seminars around the globe, and he talks about the computers of the future that sit in a shoebox under your bed at home and look after the world, then we might be dealing with a very short shelf life product here. Therefore, we shouldn't be consuming a disproportionate amount of resource and doing the TCO calculations based on lifetimes of 10, 15, 20 years. It's another economic side to the discussion on the appropriate facility to put around this equipment.
I mean, that's debatable whether that will actually happen in the future. I mean, unless there's a paradigm shift. You're worried about this paradigm shift, Alan, so that there's no cooling to be done. But let me. You've had quite a lot of time yourself, so let me go to Matt. Sorry, Alan. Forgive me. I'm the moderator here. Matt, you've been quiet for a little while. Let's hear from you on this topic. Yeah.
Well, I was going to try and give Daniel a hard time just for the sake of it, but I'm not going to. No, in all fairness, Immersion's got this in the bag big time. Direct to chip, specifically, DLCs, they've got pretty much the same advantage, I guess. It's a lot higher grade heat as standard. I did describe one scenario where we had extreme density, but I don't think that really comes into this. From an air perspective, I'd agree with Alan. That there really isn't, there isn't really a way of using the air in a sensible way. I think even if where you were trying to heat next door, say like there's a greenhouse built next door, I still don't think it would particularly work. Even if you were pushing, the supply and return air temperatures up to the max. Part of me, I know someone said something this week. I think it might have been you, John, or commented on something where. The thought of bringing compressors back into the data center in the form of heat pumps, is kind of like, that's a bit crazy. We got rid of them ages ago. For me, I think, if we continue, and I think we will, mass air-cooled installations which have liquid economization, through chillers, free cooling chillers, having a heat pump there, I see as a massive advantage to boost that temperature up. Providing that we're running grids from a clean perspective, so a higher nuclear load, which I think makes sense, and with support from renewables, having the heat pumps there to do that makes a lot of sense. One of the things that I find a problem, should we say, in terms of trying to even look at this, having worked in a few sort of projects that never got off the ground, particularly in Amsterdam, where it's a mandatory requirement, which translates to stick a de-superheater on the back of a chiller and say, hey, we've got liquid reuse. There's a lack of synergy between the data center designers and the district heating engineers. It's almost like, you look at some of the new facilities coming out, 150, 200 megawatts, and you look at the engineers that are working on them. You've got people, like Arup, NDY, all the big consultancies that are there employing data center guys to work with people that build nuclear power stations. It's a power generation sort of scale. And I don't think that actually falls into the realms of the district heating and the reuse. It doesn't get the attention it deserves. I think that's one of the reasons why, it doesn't really take off, because it's like, we're not going to get much out of it, but it's not really explored. The one thing I'm interested in is you talk about heat reuse, through absorption chillers and the like. Is there a district cooling option that we could see in hotter parts of the world? You look at India, and I'm not sure what the exact numbers are, and I don't want to get throttled for getting them wrong, but I think a huge part of their electricity use is based on air conditioning and refrigeration. Is there a bigger play there with, a centralized plant for local areas?
Yeah, so what you're saying, I think there's been this phrase that some people have used, combined heat and computation, take on combined heat and power. But maybe we should start thinking, and somebody in the chat has just said, well done, Matt, we should be thinking about this in a bigger way. Maybe we need to think about quad generation, so combined cooling, heat, power, and computation. It's all in the same, because at the end of the day, information is energy, and energy is information. It's just a transformation through these pesky little processes that generate so much heat. So, Tony, do you want to just round us off on this last this topic once and for all?
Yeah, thank you. I'm with everybody on this one, of course. The thing that, one of the foundations, one of the reasons that we formed Nexalus was on this energy reuse, recycle, circular economy story. And I know, Matt, you said Submersion has it in the bag, but we've got some tricks up our sleeves too. So our tech is 99% heat recovery as well. So we have liquid cooling, but we literally seal the server. We call it surgical cooling meets heat recovery. So we're inside the server. We're extracting all of the heat. We're giving the heat transfer devices, the heat exchangers, and all the cooling all within the server. So there is no bulk airflow in and out of our device, just water in and out. So we do by treating the server module as a control volume, a thermodynamic control volume. We've engineered it so that we get all the heat out of it as well. And the difference then is, between us and say immersion cooling, it's maybe a little less messy, but we're still stacking up in a conventional 19-inch rack with the 100%, near 100% heat recovery. So it's, it's a complementary at the very least, a complementary solution to immersion cooling. But we probably have higher power densities, and we have nice tunable control on the temperature. It's calorimetry. If we want to have hotter water, we just turn the flow rate down, provided the power's coming in. So I guess the thing for me though is that this has to happen. I mean, the clock is ticking. To me, I don't see any negatives towards reusing energy when a 20 megawatt data center can provide the domestic hot water and comfort heating for 20,000 Irish UK homes, where there's a revenue stream of annually approaching 5 million euros. I mean, there's just not a lot of negatives to it, and you see places up in Scandinavia that are decommissioning their combined heat and power plants for their district heating. 2030 is when all these sort of gas-fired plants are going to be shut off, and they're looking for this new low-temperature distributed heating grid, and they're looking for sources, whether it be a hockey arena from the compressors or data centers. They're designing now for a low-temperature district heating grid. And that's not before we get into things like food production, which I think is probably the first place that we should go. Anyway, but I guess all in all, that's why we're doing what we're doing, and that's why we're engineering these systems, is for heat recovery, but with performance profit planet. I mean, it has to be extremely high performance in order to achieve this.
So the triple bottom line, you've said it quite a few times, Tony, yeah. And I think, this leads on naturally to another topic that we should probably be considering, and that's the environmental condition, the environmental situation that we have with data centers. I mean, I remember I used to I have run over the past a conference series, and the first time I ran it, somebody who's well known in the data center industry in 2011 said the greenest data center is the one that you never build. So are we actually using all this equipment to its best capabilities? I mean, we know for example, some surveys that have been done, particularly at the beginning of the last decade, saying that utilization in data centers, in certain data centers, certain types of data centers, is very low. But let's think about this environmental aspect. So, I mean, when people do consider the cooling solution that they're going to adopt for the next build out they've got, Matt, do they actually look at the environmental impact? I mean, maybe we should talk a little bit about the embedded carbon or this aspect of the data center becoming carbon neutral. Do you have anything to say on that point?
Yeah, I mean, it's a capitalist society that we live in. At the end of the day, a lot of the large operators, I work with some of them. I guess there'll be a lot of people that on this panel will work with them as well, and people watching. They have a job to return profit to shareholders, and it's sometimes that is not so much at the expense of something else, but it's not seen as the key priority, right? So having the most efficient solution, if it costs a lot more and they're passing the cost of the electricity onto the provider as such, then or the people renting it, the colo guys, then they're not really that fussed. And I get where they're coming from on that. It's kind of disappointing from an environmental perspective, but it is what it is. We do live in a capitalist world. I know a friend of mine was moaning, it's a bit of a tangent, that Google Photos isn't free anymore. I said, yeah, but it never was going to be free forever. I said, you were more than happy to use it when it was free. He said, yeah, but they drove all the other people out, and now there's only them and Amazon Photos that I can use. But yes, capitalism, that's how it works. They've done a good job, and that's what we see in the data center industry. People are trying to drive their costs down cheaper and cheaper to get more market share. Now, Yeah, when you look at the hyperscalers that own their own data centers, I think the element of the facilities running at part load is interesting, because you can remove, and I know some of them are doing, remove things like UPS, because you can run them near to 100%, because your N plus X doesn't really matter, because your resilience is in a data center level, not on an individual component. You know, it's distributed resilience. So I think when you start looking at that, the cooling solution doesn't really bring anything into it. You know, if I'm running mine at, let's call it, you know, hot European climate at 1.2 annualized, again, PUE, sorry, it's just easy, you know, and Daniel's running it at 1.1. Yeah, Daniel's is far better from an energy perspective, but in the grand scheme of things, even including TCO and everything else that goes into it, that cost is just being passed on to somebody else. And what I'm really trying to say is nobody really cares. You know, we're all fighting to become more efficient to a problem that most of the large operators aren't that bothered about. It's just how it is. It's usually the smaller stuff that's niche that people get excited about, but we're not having a big enough effect on the mainstream large scale data centers.
Interesting point, yeah. So who's to blame for that then? At the end of the day, maybe that's something we should think about after this debate. Maybe not get into it here, but Alan, yes, go on. Please do say something. Interject at this point.
One thing that really surprised me going through this research project was when I was talking to people like John Open Compute and the GPU guys, and I was saying, we're building this, just how do you define how big you want this data center to be? What processing capacity do you require? How do you measure that those processing units against the equipment you're buying? And when I see, you know, the average density in UK co-location facilities be like 2 or 3 kilowatts, somebody once told me that the average utilization of blade servers in the UK was about 10%. That's crazy. No other process industry would survive on those numbers. However, I don't know how you get to the real number. I don't know how you calculate what processing capacity you need. It all seems smoke and mirrors to me. So we accuse the guys of not being efficient, but I don't know how they measure and plan the size of a lot of the data centers which are being constructed now.
It's actually far more complicated than that, Alan, because once you bring the software into the loop, you know, and if the software is not efficient that you put onto your data center, then, you know, it's a bigger issue, I think. But it's a good point, yeah, at the end of the day. So, Daniel, I mean, what is your take on the environmental aspect? I mean, one of the issues, again, it comes back to heat reuse. We've got a better opportunity to reuse the heat directly. And this idea of free cooling is not really free when we're chucking it into the environment. If we can displace other sources of prime thermal energy generation, and we can prove it, and surely we're in a better situation there.
Yeah, I think none of the data centers that we're building today are truly future-proof from an environmental and sustainability perspective. And there, I'm obviously going to position my technology as something that we think is future-proof. For us, free cooling means not having to design, not having design limitations with cooling an environment. I guess being able to leverage those unprecedented rack densities, be it in any region of the planet. The closed loop, no water consumption, which allows us to run the same dry cooling infrastructure, be it in Ireland or in Dubai, for example. You brought up a topic also about the anthropogenic heat flux, which I think was really interesting, but I'm also, I've been speaking quite a lot about one of the worst greenhouse gases out there, which is actually water vapor, and that data centers generate a shitload of it. Any hyperscale facility, and I'm all over the place saying it, evaporate pools and pools of drinking water, which just goes out into ambient air. So I guess Not all of them are lucky to operate in cold regions. The era of edge and 5G, I guess, is also a challenge because these bigger data centers are being built closer to where the data is consumed, which brings the environmental impact to regions where you don't have renewable energy and you have other challenge like water rights or even access to water to run these infrastructures. So that's why I refer back to the future-proofing a facility with a 20, 25-year time span is now pretty complex with air-based technologies. Just yesterday, there was an article in the Sunday Business Post that was talking about, got it here in front of me, how all new data centers built in the Dublin region will need to be capable of generating their own power because they can be pulled off the grid whenever the utility company thinks it's necessary to sustain the grid. And this was just in the newspaper yesterday. So we're going to be seeing more of this, I think. And together with restrictions on water rights and other policies that are just going to push the industry in the direction of new and friendly ways of doing things, I think we all need to think out of the box. And most of the data centers being built today, as I said, I don't think they're environmentally future-proof.
I don't think, John, just to jump in, I don't think that saying air cooling isn't future-proof or environmentally friendly. I think that's kind of a false statement, to be honest. And certainly saying the future-proofing part, rack density doesn't change. We've all looked at it for years. Now it's going to double next year. It's going to double next year. It's going to double in a decade. It never happens.
It doesn't change because you can't change it with air cooling, and no one's willing to think out of the box. So
yeah,
working and living with racks that are half empty is what people
I agree.
like.
I agree. Yeah, I agree with you.
We're already at like 40 plus without breaking a sweat. I don't see how you can credibly claim that it's an issue to look at air cooling as a future technology. I don't get it, honestly. I just don't follow the logic.
Yeah, but the issue really is that, as Daniel is pointing out here, is that there are constraints on other issues like water, I guess, and you mentioned, that's an interesting point about, we did discuss anthropic heat generation and the fact that anthropic heat flux and the fact that data centers are a contributor to that, but you're right, they do. As we use more and more economization in places, then we're obviously creating more water mist. But I'm not sure how big an impact that is. But definitely, if data is, the right to access digital information is a fourth utility, as sometimes is mentioned, then surely, the power grids in Dublin can't turn off the data center just because the hospital down the road needs the power. I mean, this is a tricky one, isn't it? What are you saying, Tony, about that? Do you know about this? About this issue?
No, I don't know about that issue. Got to read the news, but I don't think it. I think the data centers are one of the fastest growing electricity consumers on the planet. We know that. I mean, if you look at SEAI here in Ireland, the only electricity consumer that's increasing up to 2027 is data centers, and it's a lot. We're going to move from 12% to 30% of the Irish grid on just feeding data centers. I mean, and I know that not every country is going to be the same, but that is kind of the scale of it. It's a big shift in energy consumption, and how can we not, as people who inhabit this and share this planet, how can we not do what we can do? I mean, and displacing, if we use the heat to displace fossil fuels in neighboring industrial, commercial, domestic sectors, 20 megawatts. I mean, how is it that we cannot do that? It's an obligation that we do it, and it's only engineering. So we don't have to go find new physics to do this. It's just engineering. So how is it that we possibly can sit here and say we're not going to do it? Or in 2050, where we've possibly turned the corner to irreversible damage to the planet, say we didn't do it. You know, how can we not do that now? You know, it is an absolute obligation for us to regardless of it's not a big issue. We're trying to drive profits, but what about throwing profit into the mix of this decision makers of these companies where they can commoditize the heat? You know, where it enhances profit. You've lowered the PUE again. I don't like using PUE, but you've lowered the PUE. You've generated an asset. You know, there is an economical argument. You can now put data centers in Dubai if you use liquid cooling, our technology or immersion technology. I mean, there is a strong economical play to leverage liquid cooling, but fundamentally for me, it's about the energy and the reuse and the displacement. So if they buy wind power, which they're doing, these power purchase agreements, and they're actually enabling the construction of wind turbines in Ireland, which I think is great. You know, if the heat that is generated displaces fossil fuels burning in homes, then that's a full circle. That is the definition of the circular economy, because everybody wins, right? And I you know, we have to do that. We don't have time. We don't have 30 years to wait. You know, we have 30 years before things are potentially irreversible, and it's time to act. You know, the next 10 years of what we do in the next 10 years is going to be absolutely critical in the context of the planet. And we're talking about the largest growing electricity consumer on the planet.
Yeah, and the figures are all over the place a little bit on that, Tony, because we're getting studies that are saying it's 1%. Some studies are saying it's 6 or 8%. You know.
No, Nature just did there's a publication in Science, just recently, that tidied up a lot of those numbers, right? But it's about the growth, and it does change from location. So those numbers are published in Science now. It's solid.
Okay, I'll look that one up. Yeah, Alan, please do interject here.
When we come back to the actual engineering of solutions, we've got to accommodate two things. We obviously deal with a lot of people who've got a lot of legacy equipment that we can't change. So what can we do to improve their efficiencies and their energy use? Okay. Without necessarily radical reconfiguration of the existing equipment. And then the new business, much of my work is out close to John and the guys from Luleå in North Sweden, Iceland, Norway, is where people are obviously relocating the processing power close to hydropower stations or geothermals, because they can buy electricity at 1 or 2 cents a kilowatt hour. You know, this is not about an eco debate. This is a pure financial debate. But whilst they are moving to that area, what it does mean is they're not forcing fossil fuel power generation to continue in other parts of Europe or the world. And there's another challenge, as John's already mentioned, about the efficiency of software. If the sector can start developing software-defined data centers where we shift the processing to the lowest environmental impact area of the world, and we have that segregation between low latency and high latency work, non-sensitive, critical, non-critical. If we start segregating all that and get that sorted out, we could massively reduce the actual amount of processing and IT equipment that we've got sitting in some of these high environmental impact locations in the world. So we take a bigger view of where does that data actually get processed or that data stored. Okay,
good point. I mean, you brought it round to engineering, Alan. I mean, at the end of the day, I said at the beginning that we would have maybe some consensus on opinion here, but at least we got a little bit of divergence of consensus of opinion here. But Matt, I mean, I guess, I mean, Airedale have worked both with liquid and air, but I mean, there must be situations where you would say, wait a minute, this engineered solution, it's better liquid or it's better air. Does that happen very often? I mean, what would you say there?
I'd agree with the general feeling of that. Yeah, there's always going to be a better solution. You know, even if it's direct to chip immersion. The nice thing, I mean, I get where, you know, the immersion sort of cooling companies, Daniel with Submer, you know, Rolf for the Spiritas are going on wide-scale adoption, which, you know, it might happen sooner than we all think. You know, I'm not going to be one to say that it's not going to happen, but I see that currently being more of a drop-in replacement for high-density requirements rather than being seen en masse, and I think that's really cool. I mean, I know with the isotope stuff, just an example, there was a film animation studios doing rendering, and they were having loads of issues, and they had this like sort of cupboard that would turn into a bigger cupboard that was screaming and upsetting everybody. They turned it into one rack that just sat in the attic with a little dry cooler on the roof. It was awesome. You know, that's pretty cool. But en masse, I think air cooling is, we all know, it's pretty much the standard because it's cheap, it meets the requirement, and it's easy to deploy. So I don't think that's really changing.
Okay, yeah, thanks, Matt. We're getting close to the time is up. So, Tony, yeah, you're an engineer. Surely you would advocate air cooling when there's the solution requires it.
Yeah, I mean of course, as an engineer, you know, but it depends on what you're engineering to. You know what I mean? Like, I can engineer an air cooling system in a data center. I can engineer a cooling system for an LED headlamp in a car. I mean, that's what I do for a living. So if the parameters that I'm given as an engineering designer, you know, being a scientist and an engineer, I will come up with the best solution given that box that I'm given to engineer and the constraints from the company or the industry.
Okay, but I mean, we started off with.
If you don't have that constraint, then liquid cooling is cooling can do all of those things, but the secret sauce that we have from Nexalus is that we're using liquid cooling both as direct on chip and as integrated air water heat exchangers, 1U air water heat exchangers that cool the air and cool all the RAM and all the other stuff in a sealed server. So, I mean, it's not that much of a mental step towards what you're doing today and what the Nexalus one is offering. It's just that we've kind of decoupled the rack from the data hall air by doing it this way. So it really isn't that big of a mental step for me from what Matt's talking about, to be quite honest.
Yeah. I mean, Alan, you've got to admit. Yeah, go on.
What has stopped? I mean, liquid cooling has been around for a long time. John's been working on it for as long as I've known you. It's like 100 years, John, right? Okay. What are the barriers to people adopting it?
Daniel, yeah. What are the barriers?
I can help with that. One of them is obviously, and probably the biggest one, is actually the hardware vendors getting their heads around it and actually supporting and designing systems which are optimized and warranted in immersion cooling. And I think that's been the biggest challenge up until a year ago, probably. When it was really hard to find major server manufacturers providing support and warranty for standard systems, something which today is completely different. You'll see all the major suppliers, hardware distributors, etc. You can get hardware from any of the major vendors, supported and warranted in immersion. And I think that's why we've seen a major acceleration in the adoption of immersion cooling. And also something very associated to the growth in the OCP community, where there's been quite a lot of immersion done, as everyone knows.
Yeah, I mean, I think on that point, Daniel, that's a very good point. I mean, liquid has arrived because the IT manufacturers are now kitting their equipment ready for this. So we're running out of time now. I've got 1 minute left, so I need that time to thank all of you for this interesting debate. I think we could go on for another hour because there's a load more questions. There are some questions in the chat that I don't think we even touched upon about reliability and cost, etc. But let me say thank you to Tony and Alan and Matt and Daniel in Barcelona for being such good sports. It's not really air versus liquid, is it? It's but there are some clear engineering examples of when one is better than the other, perhaps. You know, but it's still a long debate. But liquid has arrived. That's what I would leave you with. So, Hugh, you need to say something. Yeah.
I do. I just wanted to say, first of all, thank you all for a fascinating debate. I hope to see this live at Data Centers Island in November next year. I think we could probably run a whole day on this and not get to the end of it. It's interesting to bring in the air grid and their recent announcement. It's interesting to bring in heat networks and district heating, and joined up thinking. One thing is, from the sounds of it, all of you have the capability to do that. It's just I'm not sure the powers that be are already going down that route. And I just hope that that changes for society, whether that be air-cooled or liquid-cooled. I'm not going to debate that one, not in this company. Just wanted to say thank you to you all. And for anyone who wants to watch this, it will be on demand, probably from tomorrow, or via the Data Centers Island website, which is www.datacenters-island.com. And again, Alan, Tony, Matt, Daniel, and to you, John, thank you all very much indeed.
Thanks very much. Thanks
everyone.
to all you guys.
Cheers, John. Cheers, Hugh.
Bye-bye now. Bye.
Thanks.